What if I told you that one of the most sophisticated pieces of engineering in human history isn't in some modern lab, but was being perfected by our ancestors 64,000 years ago? When you think of a bow, most of us picture this: a simple toy, a bent stick and a piece of string. It's an image that's been locked into our collective imagination. But that simple image? It's a historical lie. A profound underestimation of our ancestors' ingenuity. Archaeological evidence tells a much different story. A story of a prehistoric superweapon, an engine of change built with a complex toolkit, and an understanding of materials that was revolutionary. The bow and arrow weren't just a simple tool. They were one of humanity's first examples of a complementary tool system. Think of it like a lock and a key. One is useless without the other, but together, they unlock a powerful new capability. They were separate, sophisticated parts designed to work in perfect, deadly harmony. Today, we're going to follow their ancient blueprint. We're going to deconstruct this simple weapon to reveal the forgotten technology, the specialized tools, and the advanced engineering principles required to build a weapon that dominated hunting and warfare for tens of thousands of years. Section 1. The anatomy of a superweapon. The idea of the bow as a primitive tool is just deeply misleading. It suggests it was an obvious invention, a lucky accident. The reality is that a functional, powerful bow is a complex machine designed to store and release a massive amount of energy, much like a battery stores and releases electricity. Building one from scratch required planning, abstract thought, and technical skill that fundamentally challenges our perception of so-called primitive man. The clues for this sophistication aren't just speculation, they're written in stone. In places like Sabudu Cave in South Africa, fragments of bone and stone points tell a story that pushes the origin of archery back to at least 64,000 years ago. We can't find the bows themselves, since wood and string rot away, but the arrowheads and the damage on them strongly suggest they were shot from a bow. Recreating the process through experimental archaeology reveals what it would have taken to create a bow and its arrows. Our ancient ancestors needed a whole shopping list of different raw materials, binding agents, and incredibly strong glues. The process wasn't the work of an afternoon. It was a project that demanded foresight and an understanding of cause and effect. It required the ability to see not just a piece of wood, but a future machine. This weapon system represents one of humanity's earliest and most enduring engineering traditions, passed down for millennia. Section 2. Reading the ancient blueprint. The journey to create this superweapon begins not with an axe, but with the mind. The first and most critical step was selecting the perfect piece of wood. Ancient bowmakers were part botanist, part material scientist. They didn't just grab any branch. They carefully examined a tree, reading its life story in the grain, the knots, and the wood's shape. This initial choice was everything. The bowyer had to find the perfect orientation for the bow within a larger piece of wood, or stave. They had to decide where the belly, the side facing the archer, and the back, the side facing the target, would be. Imagine pulling a rubber band that's tension, and it's what the back of the bow endures. Now imagine squashing a spring that's compression, and it's what the belly withstands. The wood has to do both at once. A mistake here, a failure to read the grain, and the bow would catastrophically fail, splintering into useless shards. This single decision reveals a deep, intuitive understanding of physics. Once a stave was chosen, it often needed straightening. Some green woods, like willow, could be carefully steam bent over a fire. This wasn't a crude process. It required using fire like a precision heat gun, not a bonfire, patiently heating the wood just enough to make it pliable without scorching or weakening its fibers. This shows a mastery of fire, not just for warmth, but as a precise engineering tool. Section 3. The prehistoric toolkit. With the wood selected and prepared, the long process of shaping began. This is where a reconstructed, specialized toolkit of the ancient engineer comes into play. To turn a rough stave into a high-performance energy storage device, you have to remove material with incredible precision. A whole progression of tools was used, each one perfect for a different stage of the process, much like using different grits of sandpaper. First came the heavy work. An axe or an adze was likely used for the initial rough shaping, like using very coarse 6-0 grit sandpaper to quickly remove large chunks of wood. These early axes weren't the balanced, razor-sharp tools we have today. They required immense skill to wield with any accuracy. Next in the sequence was probably a sharp flint blade. This tool, acting much like a modern spokeshave, would be used to remove more moderate amounts of material, refining the shape. This was the medium grit stage. The bowyer would begin to carve the graceful taper from the handle to the tips, working down the wood with controlled, steady strokes. For the finest, most critical adjustments, they probably turned to a flint scraper. This was their fine grit sandpaper, allowing for the removal of the tiniest shavings of wood. This wasn't guesswork. The bowmaker would flex the limbs, feel for stiff spots, and then meticulously scrape away material to achieve a perfectly balanced bend. Finally, to create the nocks, the critical notches at the tips that hold the bowstring, a serrated flint blade may have been used, cutting with absolute precision. This toolkit shows a clear, methodical process, where each tool had a specific job in the grand project of the bow's creation. Section 4. The chemistry of power. As the millennia passed, this technology only got more advanced, and perhaps the most astonishing evidence of our ancestors' scientific minds is found not in their tools, but in their chemistry. The construction of the most powerful ancient bows, known as composite bows, was impossible without sophisticated adhesives. One of the most remarkable of these was birch bark tar. This wasn't a simple substance. To create it, ancient engineers had to heat birch bark in an oxygen-starved environment, a process known as dry distillation. It's like using a pressure cooker on the bark, heating it to hundreds of degrees without it bursting into flame, causing it to break down into a sticky, waterproof, and incredibly strong black tar, a primitive epoxy that was light years ahead of its time. Another critical substance was hide glue, rendered by boiling animal skin, bones, and tendons. This glue provided immense strength, but its real genius was in its application with another key material: sinew. Animal sinew, from the tendons of animals like deer, was laid in layers along the back of the bow. When attached with hide glue, this sinew acted like a powerful set of elastic fibers, storing massive amounts of energy. A sinew-backed bow was exponentially more powerful than a simple wooden bow of the same size. It was a true composite material, prehistoric fiberglass, combining a material good at resisting compression, wood, with a material good at resisting stretching, sinew, all held together by carefully engineered glue. If you're finding this look into the hidden genius of our ancestors as fascinating as we do, take a moment to subscribe. We're dedicated to uncovering these lost technologies and rewriting the story of ancient engineering. Section 5. Engineering for performance. With the bow shaped and the materials prepared, the project entered its most crucial engineering phase: tillering. Tillering is the process of teaching the bow how to bend. An improperly tillered bow will have stiff and weak spots, concentrating stress and increasing the likelihood of breaking. It's like having a team of rowers, where some aren't pulling their weight. The few who are doing all the work will tire out and fail. A perfectly tillered bow, however, bends in a beautiful, uniform arc, distributing the load evenly so that every part of the wood does its fair share. How did they do this without modern tools? Experimental archaeology suggests they could have built a rudimentary tiller. By placing the bow's tips on two logs and carefully applying pressure to the handle, the bowyer could see how the limbs flexed. They would then mark any stiff areas with charcoal and return to the meticulous work with the flint scraper, removing a tiny amount of material before testing again. This was an iterative process of testing, observing, and refining the very heart of the engineering method. Once the bow was tillered to perfection and the nocks were cut, the work still wasn't done. The bow had to be trained. It's like stretching before a big workout. You don't just go and lift the heaviest weight possible. The wood fibers need to gradually acclimate to the immense stress. The training process would begin with small, partial draws. After 10 to 20 repetitions, the draw length would be slightly increased, and the process repeated. This careful, patient training continued until the bow could be drawn sufficiently to shoot an arrow, without shocking the wood into failure. Section 6. The payoff. A prehistoric superweapon. Finally, after dozens of hours of work, all the components come together. The perfectly tillered wood, the advanced composite materials, the precisely cut nocks, and the hand-twisted bowstring. What stands before you is not a stick. It is an engine of war, a silent, long-range weapon that changed the course of human history. When tested, the power of a properly reconstructed ancient bow is staggering. It acts like a deadly natural battery, storing the archer's muscle power in its limbs and releasing it in an instant. Fired at ballistic gelatin, which simulates muscle tissue, the arrow doesn't just puncture, it penetrates deeply, creating a devastating wound channel. Against replica shields or leather armor of the period, the results are just as decisive. The energy is transferred to the arrow with shocking efficiency, turning it into a projectile capable of taking down the largest game from a safe distance or piercing an enemy's defenses before they could even get close. For thousands of years, the bow was the great equalizer. It allowed a single hunter to do the work of many. In warfare, it was the ancient equivalent of an assault rifle, a force multiplier that rendered close-quarters weapons obsolete. The ability to project lethal force from hundreds of feet away was a revolutionary leap, an advantage so profound that the secrets of its construction were carefully guarded and passed down through generations. Conclusion. So, is the bow just a simple stick and string? The evidence proves otherwise. It's a testament to the mind of the ancient engineer. It's a precisely shaped stave, chosen with the knowledge of a master carpenter. It's a specialized toolkit of instruments, from heavy-duty axes to fine-tuning scrapers. It's a marvel of prehistoric chemistry, utilizing complex glues and composite materials to create a device of incredible power. And it's a triumph of engineering, brought to life through a patient, iterative process of tailoring and training. The creation of the bow was a cognitive landmark. It required abstract thought, long-term planning, and a deep practical understanding of physics. The next time you see a bow in a museum or a movie, remember what you're really looking at. Remember the specialized tools, the complex,